Welcome back everyone. We've looked at how we might implement in a heap, and we used an array implementation to do that rather than using, say, a tree implementation. Now let's look at some of the operations. In this video we're going to cover the add operation. Now if we recall, when we're adding a new element, say 18, what we first need to do is add it in this bottom here so that, again, that it's complete. So in this example, we're going to have to add it to the right child of 15. And then we're going to have to rise it up into its correct position. To rise, we need to compare with the parent, if any. So the algorithm for add, if there is no space, return false. Otherwise, if there is space, we're firstly going to have to put the element at the bottom of the heap. While the heap order is broken, element is smaller than its parent, we need to rise swap the new element up to its parent and then finally return true. We could have decided to resize when full and returned nothing. So that's another option, but just in this example we're going to assume that we're not going to resize the heap when it becomes full. So let's look at a concrete implementation for add. So if we have space left, so it's not is full, if we have space, then we're going to add 1 to the length to signify that we're adding a new element. We're then going to add the new element, and that's as easy as just, making sure that we at the length add the new element. It's sort of like the append operation on a list. But then we're going to rise, and we're going to pass it the current element as well that we're rising it from. And then we return if there's any space left, just to say if it's become full, then obviously we can't add any more elements. So let's have a look at rise. So we're rising the element at index k to its correct position. Now remember, when we're rising up from element k or position k, all we need to do is divide by 2 to work out what the parent is. So while k is greater than 1, so that's a check to make sure that we haven't hit the root node, or we're not at the root node, I should say. And then we want to see if the current node is bigger than the one above it. So in this case, if k is greater than 1, obviously it will have a parent. And the parent is smaller. So if the parent is smaller, then that means we need to make sure that we have to rise it up. So in this case, we need to swap them. Essentially what we have to do is keep rising it up while we're not at the root node, and whilst it's not in the correct order. So this check hasn't been enforced to make sure that we have got an element greater between 1 and the length of the array itself, but in practice you'd probably have an assertion just to make sure that you enforce that correctness, that it is in between 1 and the length of the array. So let's step through this example line by line on how this algorithm works for the add. So essentially we've got our array here, and again starting from 1, and we want to add 18. So 18's going to be added in to the correct position here, right? So let's firstly check if it's full. No, it's not currently full, so we currently have space left. We're going to add 1 to the length, so that's now the position of where we want to add it in. So we add the position at that element. So 18 gets added there, but the problem is we need to now heapify, or we need to fix it so that it's a correct heap. So that means we need to rise and keep calling this, and we've done this in a loop, but you could do it recursively as well if you wanted to. But the idea is we keep rising up until it's in its correct position. So in this example here, we're going to go, it's not at the root node yet, and it's still greater than its parent. So then we're going to swap the elements, and then we're going to divide by 2. So then we update k, what we're currently looking at, to this node here. So now we look at 18 again. It's greater than 1, this position here, which is 5, and then we're going to compare it with 2, which is this element here, 15. And again, because 18 is greater than 15, it's going to then perform the swap. So we swap those elements and then we divide by 2. Now k is equal to 2. So we're looking at this element here. And now we see k is greater than 1. We haven't hit the root yet, but at this stage, 18 is not greater than 20. Therefore, this condition will fail. And we've got it in its correct position. It will return back to here. And then it will do return whether there was space left. So basically to say whether it was successful or not. And then in this case, obviously, it was successful to add the new element. So an alternative implementation for add, no swaps, just shuffle parents down to make a hole for the new element and then put it in the hole. So again, we're going to see if there's space left. If it has space, we add 1. That's pretty straightforward. But this time, what we're going to do is the element is going to be the element returned from rise. So returns the whole, if we like. So the idea, it does all the swaps and then just inserts it into its correct position in the heap. And then returns space has left. So again, rise is going to be pretty much the same here. So it's going to shuffle except it's going to shuffle the parents down this time rather than swap them. And then again, it's going to then divide by 2, so it looks at the next one and return k, because the point is we need to know the final position of where that hole is, so then we can insert it into that position. This is faster but less clear. So again, it's definitely more efficient, but it's a little bit harder to understand. So obviously there's pros and cons for this particular approach. So equally, we could look at another alternative is if we just eliminated the modularization and just put it all into one function here, we can see obviously when we've tried to calculate the position k, that's basically what the rise was doing here. It was calculating that and rising them up. Then you can see whilst this will be more efficient, we don't have to do the function call, we don't need to put the arguments on the stack and save any extra registers if you consider MIPS. Basically, it'll be more efficient, but it may be harder to maintain because it hasn't been well modularized. So obviously, making things more efficient and faster, whilst it may make it quicker, doesn't always make it easier to maintain. And another argument is we might need to change the priority at some point. So we may need to use rise in another scenario in case perhaps, for example, the priority of a node has increased and we need to rise it up. Then we may need to use the rise function as well. So I guess the point is rise and sync are used quite often, not just by add, but also get max. So the point is it's good to keep those functions for maintenance, and the fact we'll probably reuse them in other situations. So the complexity of add, start with the first version and assume there is space. We put an element at the bottom, and while the heap order is broken, we swap the new element with the parent. First one's done in O1. And we have to obviously compare each element, but to do this swap's done in O1 time. So let's consider how many times the loop can iterate. Well, the loop 2 can iterate at most the depth times, which is log n. After depth iterations, the new node is at the root. And remember that it's complete, so that's why we can guarantee that the depth will be equal to log n. So best case is O1 plus compare when the element is small or equal to than its parents. That means it just needs to do the comparison. Worst case is when we have to do O1 times log n multiplied by the compare. So as we're going, basically the depth times compare is probably the easiest way to simplify that, and we know the depth is log n. So let's consider, is this the same for all versions? And yes, it doesn't matter whether you're doing the shuffle implementation or you're doing the swap implementation, they're still done in O1 time because you still need to go through all those nodes to compare against them anyway. So it means that there's less copies in the version where you just do a single swap, but it doesn't affect the big O complexity. That's the end of this video on how to do the heap implementation for add. In the next video, we're going to do the getMax method based on the heap implementation. We'll see you in the next video.